dark matter, we'll offer some commentary on the results presented this morning and some more thoughts about this whole issue of where is the rest of the universe. So with that, we'll take a moment to do a little bit of technical wizardry here and switch computers, and then I'll turn it over to Catherine Hamans. We're looking good, promising so far.
Yeah, thanks, Rick. So today we're unveiling the largest maps of dark matter ever imaged, and what you can see here on the slide is just one out of the 4 dark matter maps that we've made. Over the next 10-15 minutes or so, Ludovic van Verbeke and myself will be telling you about how we made these maps, but we're going to start off with why it's important. Now, did you know that only less than 4% of the universe is made up of the matter that we're familiar with on Earth? The stuff that you and me, the Earth, the Moon and the Sun is made up of. Those sort of particles comprises only 4% of our universe, and the rest is dark. Now what I'm showing here is a computer simulation of what we think the universe would look like if we could see dark matter. This is our theory of what dark matter would look like. So our theory is that it would form these long filaments, a giant cosmic web with knots, and we also have a theory that it's the dark matter in our universe that's dictating where and when the galaxies that we can see form. Now, the dark matter isn't alone in the dark universe. It has a sibling that we call dark energy. Now, there's a giant cosmic battle going on in our universe at the moment between these 2 components of the dark sector. Dark matter is the strong gravitational force. It's pulling all these structures together, forming this giant cosmic web. Dark energy is acting in the opposite sense. It's stretching space apart at an accelerated pace, effectively stopping these structures from forming. Now, I'll be very honest with you and say we know very little about the dark universe. We don't know what the dark matter particle is. We don't know what this dark energy is coming from. And it's very widely believed that our final understanding of the dark universe is going to have to invoke some new physics, something that will forever change our view of the universe. And what the CFHT lensing team is presenting at the AAS today are really the first steps towards reaching this goal of understanding the dark universe. Now, I've told you that, that dark matter is dark and invisible, so how have we made these maps if it's invisible? So what I'm showing here now is a cartoon movie of the technique that we're using, which is called gravitational lensing. Now, what this movie is illustrating is light coming towards us from a distant galaxy here, and that light is bent by the gravity of this lump of matter in the middle. Einstein's theory of general relativity told us that mass bends space and time. So when light comes towards us through the universe, if it passes some dark matter, its light gets bent, and the image that we see of the very distant galaxy gets bent and distorted, which you can see here in the movie. So we've got a nice distant galaxy, and you see it gets bent in a sort of a banana shape. And this is the signature that we're looking for. You can imagine that dark matter is leaving its signature on the images of very distant galaxies. Here's another cartoon. In red you can see the dark matter, and in green those are the galaxies that we're observing, and their light has travelled through the dark matter and has been distorted. Now in this project we've analysed the images of over 10 million galaxies. Their light has taken almost half the age of the universe to reach us on Earth. With a very careful analysis of these images of these 10 million galaxies, we can unravel and uncode the information about the path that this light has taken through the universe, and that tells us where the dark matter is and how much of it there is. The Canada-France-Hawaii Telescope Lensing Survey is the data set that we're using. This really is the state-of-the-art in surveying the dark universe. For over 5 years, the Canada-France-Hawaii Telescope, which you can see in the bottom right-hand corner, it reserved the best weather conditions in order to undertake these legacy observations. In each season, winter, autumn, spring and summer, this telescope imaged a different patch of sky that's roughly the size of your palm on the sky. and this is 100 times larger than any previous deep survey. We're imaging in 5 different colours, just as if you're listening to a woodwind quintet, you're not going to hear the full music if you just listen to the clarinet. If we want to get a full information about the universe, we need to look at it in Technicolor. Now, the results that we're presenting today have only been made possible thanks to advances in our data analysis techniques. It was a wonderful team of a truly international team that did this work, and I'm delighted to say a whole bunch of them are in the room. And this afternoon we're going to be presenting a series of results. But this morning we're just focusing on our real highlight result, which are the largest maps of dark matter in our universe. And I'm going to pass over to Ludovic van Berbeke to tell you more about them.
Thank you very much, Catherine. So I'm showing you this map as an illustration of the problem we are addressing here. Searching for dark matter in the universe is a bit similar to searching for where people are living on Earth, just looking at a picture of the Earth at night. That is, if you think that most people live where there is most of the light, looking at this picture, you know that's wrong. You know that most people don't live in North America and Europe. Most people live in Asia and Africa. So it's very similar to the problem we are addressing with observations. We are trying to find where dark matter is, and if you think that dark matter is mostly located in galaxies where there is bright stuff, well, there is a chance that you'll get the thing wrong. So it's very important that we can use gravitational lensing to identify, to map dark matter, because this is the only way we can actually access the dark sector. So gravitational lensing is really a unique tool and very crucial and very important for this kind of study. So this is the largest map, one of the 4 maps of dark matter ever done by our community. So what this map is really exceptional in many ways. First of all, it shows, so this is a fake color rendering of the dark matter distribution, where in yellow you see the highest mass concentration of dark matter, and in blue, shaded blue and pink, the lowest concentration. And what this map is revealing to us is something we kind of expected for a very long time from theoretical studies and from numerical simulations, is that dark matter is mostly concentrated in dense and compact groups that you see the yellow dots here. And between those high mass concentration, space is vast and nearly empty of matter. Well, there's not much matter between those high concentrations. To give you an idea, this field is about 8 by 9 degrees big on the sky, and in terms of physical scale, the typical average physical scale across that field is roughly 1 billion light years. So we are talking about very large scale. And what we see here is very similar to the simulation Catherine showed at the beginning, that is dark matter is concentrated in those lumps, and the rest of the matter stretches as filaments between the concentrations, and you see the big void regions as well between them. Now, if you focus on the highest mass peaks, what you see here, looking at the optical data, those are really hosting giant monsters, clusters of galaxies. I'm showing you 3 of them here. Those are really, really big clusters. The mass of those clusters are probably over 10 to the 14 solar masses, total mass. So we are talking about really big galaxy clusters here. So thinking about, so dark matter map, the same map is shown here in a different color rendering. What we see also here for the first time through this picture refers to the big cosmic battle that Catherine mentioned before, which is this battle between gravity, which wants to pull everything at small scale under the force of gravity, as opposed to dark energy, which wants to stretch everything apart at large scale. So this is what the dark matter map also is showing us. Dark energy wants to pull everything away from each other at large scale, but at small scale, dark matter wants to cluster and concentrate in big clusters of galaxies. Now let's have a slightly closer look to how dark matter compares to the mass distribution from the galaxy distribution. So this is the dark matter map, and the next slide is showing the expected mass distribution if you were thinking that mass was only distributed within galaxies. So blue is dark matter and pink is the mass within the galaxies. And the next slide will show you a dissolved fondu enchaîné between the two images, and you'll see how well dark matter and galaxies match to each other. So going from back and forth between from one to another, you see that where you have big clumps of dark matter, this is also where you have big clumps of galaxies. And also where you have voids in dark matter, this is where we have regions with very little galaxies in them. You see, if you look at carefully the image, you can identify at least 3 gigantic voids that cover 100 millions of light years across on this image. So this is the first time we actually see this in dark matter. This has never been done before. And we are very happy that this is very similar to what we've been expecting. The next slide is showing you the full 4 maps we've been analyzing with gravitational lensing technique. So the top left image, the largest one I just discussed, the winter field, is the top left image. And the small inset at the center, the color inset at the center, shows you the largest dark matter map that was available until now. We are improving in terms of scale over which we can map the dark matter. We are improving previous results by 2 orders of magnitude. We can map angular scales which are 100 times bigger than was done before. And also as a comparison, you see the size of the moon on the sky. So really, the whole field is pushing towards mapping dark matter at even larger and larger angular scale. This is the whole goal in dark matter searches. And the reason for that is if you really want to put strong constraints on alternative physics or new physics behind dark matter and dark energy, you have to improve your statistical measurement as much as you can. And the only way to do that is to reach larger and larger angular scales. So basically over the next decade or 15 years, astronomers and cosmologists interested in dark matter studies will work very hard in trying to expand this kind of analysis to the full sky. So I'm finishing here telling you about our CFHT Lens session we have in the afternoon. You'll hear about the scientific details of these dark matter maps. You'll hear more about constraints on dark energy we got from these maps. You also hear a very interesting new study about testing gravity at large scale. So the theory of gravity we know is working well, is Einstein's general relativity theory, but it has never really been tested directly at very large angular scale. So you'll hear something about this afternoon. And also you'll hear more details about how galaxies and dark matter are related to each other. This is a complex relationship, the galaxy versus dark matter, and there is lots of analysis going on here to understand this relationship better. Thank you very much.
Okay, thank you. Now we're going to switch scale. Actually, Ludo, you gave a very good introduction to the next talk, because Sukanya Chakrabarti from Florida Atlantic University is going to now look at the relationship between where the dark matter and the visible galaxies are located, but now on the scale of a single galaxy.
About a new probe of the distribution of dark matter on galactic scales. The basic idea is that the ripples or disturbances in the cold gas on the outskirts of galaxies can be used to trace the depth of the potential well of the dark matter halo. In this work, I'm actually building on last year's paper that we presented at the WS press conference, where we found that we could characterize dark matter-dominated dwarf galaxies. Okay, thank you. From analyzing the gas surface density map, what's shown on the left is the atomic hydrogen map of M51, and we found that analysis of the Fourier amplitudes, that is the strength of the response, allows us to characterize the mass of M51 satellite and its location. I'm building on this now to additionally look at the shape of the disturbances. And I find that the potential, that is the disturbances that form, the shape of the disturbances, actually mirror the potential well of the dark matter halo. I'll just review briefly last year's presentation, since I'm building on this here. The movie shows the gas density response as M51 is interacting with its satellite. On the top is the optical image of M51 and its satellite. As you can see, M51 has an optically visible satellite that sits close to the tip of the short arm. This is the atomic hydrogen map of M51. And by fitting to the Fourier amplitudes of the data and comparing to a set of simulations, we were able to accurately determine the mass of M51 satellite and where it is. I marked with crosses here the location of the center of the galaxy and the satellite. And at the time when we had the best fit to the Fourier amplitudes, the satellite sits close to the tip of the short arm, as it does in the real galaxy. So I'm building on this now to ask, what can we figure out about the distribution of dark matter in the larger spiral galaxy? Of course, since the 70s, we've known from observations of flat rotation curves that galaxies have massive dark matter halos. But there are very few probes that allow us to figure out how it's distributed. Theoretical expectations from n-body or dark matter-only simulations suggest that it has a universal power law form that was first articulated by Navarro, Frank, and White. The density follows a r to the minus 1 profile interior to the scale radius and follows a r to the minus 3 profile exterior to the scale radius. This is the density that the dark matter follows in the spiral galaxy. Now, for a given mass halo, specifying the scale radius is equivalent to specifying the density profile of dark matter. So within this context, the question we want to ask is, how can we get the scale radius of specific spiral galaxies? How can we develop an observationally motivated probe? So I'm building now on previous results for M51, so I'm going to use the derived satellite mass and pericenter approach distance, as we found those numbers to be observationally corroborated. And I'm going to vary the density profile of dark matter in the primary spiral galaxy by varying the scale radius, which is equivalent to varying the potential depth. And as you can see, it changes the resultant disturbances dramatically. On the left is a large scale radius case, a scale radius of 32 kiloparsec, and moving down to lower and lower scale radius cases. If your scale radius is very large, that means the dark matter follows a very shallow density profile all the way out to the edge of the gas disk. If it's very small, like in the 11 kiloparsec case, it switches and follows a steeper density profile. And steeper density profiles are more effective at holding on to their stuff, and therefore they have a much more tightly wrapped spiral planform as opposed to ones that are more shallow. You can express this, what you're seeing here in the images, you can express this quantitatively by looking at the phase of the modes, which tells you about the shape of the spiral planform. That's what I'm showing here on the left, the phase of the m=1 mode as a function of radius for the 3 cases that I showed in the last slide. The black line shows the phase of the large scale radius case. The red line shows the phase of the 11 kiloparsec, the low scale radius case, and the green is the intermediate scale radius case of 17 kiloparsec, overplotted with the data of M51, overplotted with the phase of the m=1 mode of the data. And you can see that the 17 kiloparsec case is the one that has a shape that agrees most closely with the data. The other two have a gradient in the phase that is either negative or positive. You can understand this physically a little bit more by looking at the phase as a function of a dimensionless radius. That is, by plotting it as a function of the radius divided by the scale radius. And in these units, you see that interior to the scale radius, this is the plot on the right, you see that interior to the scale radius, the phase has a negative gradient. Exterior to the scale radius, there's a positive gradient, and there's a transition region close to the scale radius. And that is what you see on the left plot as well, where you're probing regions interior, exterior, and close to the scale radius. So if you can observe this transition region with long baseline H1 observations, you can determine the scale radius of specific spiral galaxies in the local volume. So I'll summarize by saying that I find that ripples in outer gas disks serve to act like a mirror of the underlying dark matter density distribution. They reflect the underlying dark matter density distribution. And in particular, you can use the shape of the disturbances, the phase of the modes, to determine the scale radius of specific spiral galaxies. The shapes that form will be loosely wrapped if the profile of dark matter is very shallow, and will become more and more tightly wrapped as you steepen the profile of dark matter. When I applied this method to the Whirlpool galaxy, I found that M51 has a scale radius of 17 kiloparsec, which is interesting because that's consistent with expectations from dissipation lists, that is, dark matter only cosmological simulations. And what we're using here is a baryonic tracer. So this is a new method to characterize the dark matter density profile. It is complementary to lensing, which the presenters have talked about before, and what is in progress now with a number of collaborators is applying this method to a large number of galaxies in the local volume to come up with the statistical determination of the scale radius of spiral galaxies in the nearby universe. Thank you.
Okay, thank you very much. And now we'll have some commentary from Rachel Mandelbaum, who's at Princeton University and Carnegie Mellon, and she'll talk about how we're going to use results like these and others to unveil the dark side of the universe.
Thank you. So my role up here as somebody who is not involved in any of the measurements you've heard about is to give you some of the broader context of what these results mean and how they stand in comparison to other measurements out there. So to give some of the broader context, dark matter has been a part of our cosmological model since roughly the 1970s. So in the 70s, there were observations of spiral galaxies, specifically their rotations. It was found that the outer parts of the spiral galaxies were rotating too fast. It seemed that there was too much matter in those galaxies than could be explained by simply looking at the stars. And so this was used to infer the presence of some dark matter component in those galaxies. Many other observations have corroborated that result, and we now have a cosmological model in which, as you've heard, most of the matter is in fact dark. Catherine showed you a very nice illustration of some of the theoretical predictions for what the dark matter distribution should look like. The so-called cosmic web, which has these collapsed clumps called dark matter halos, and also larger scale connections between those halos and underdense regions called voids. Of course, this is by its very nature tricky to observe because the dark matter is dark. We need to find indirect ways to infer its properties. So now I'm going to talk about the two results you've heard about specifically, and I'll just go in order and start talking about the CFHT lensing results. So weak lensing is a useful way to study the dark matter because the lensing deflections of distant galaxies, the lensing distortions of distant galaxies, are affected by all the matter as that light propagates to us, all of the matter, including the dark matter. As you have heard, the dark matter map coming out of this survey has a tremendous cosmological volume, and that's a consequence of two things. First of all, the survey has a reasonably large area, and second, the survey is fairly deep. So to put it in context, there have been deep surveys such as the Cosmos survey that Ludo showed a comparison with. That survey is also very deep, like the CFHT lens survey, but it covered a very small area because it was based on space-based data, which is difficult to get in very large amounts. So in contrast, the CFHT covers a larger area and therefore a much larger volume. To make another comparison, this Lund Digital Sky Survey has been used by many groups, including myself, to study lensing, but it's an extremely shallow survey. And what that means is that those observations are limited to the relatively local universe to pretty late times. And the advantage of this CFHT lensing survey is that it's deeper, and therefore it allows us to study results that go back to the time when dark energy started to become important in causing an accelerated expansion of the universe. Okay, so with that context in mind, these lensing mass maps that you've seen are very important. They're a very important test of our cosmological paradigm on the cosmological scales. The large-scale structure that you saw in these maps shows a lot of the expected features, namely it shows that clumping, that sort of cosmic web appearance. And we see that clumping, the dark matter halos, seem to correspond to fluctuations in the light, not perfect one-to-one, but in general a statistical correspondence, as we expect. So these results could be used as a test of our dark matter, of the dark energy, and even the theory of gravity. Moving on to Sukhanya's results. So in some sense, these results go back to the origins of the discovery of dark matter, which, as you heard, was in spiral galaxies. So in this case, what's being observed, the spiral galaxies, is similar, but a different observational method is being used, using the disturbances in the disk to infer something about how much dark matter is there. So an important thing to keep in mind about this result is that it allows us to see the dark matter distribution in individual galaxies. So that's an important contrast with the lensing. So for the lensing results, it's possible to study the dark matter distribution in individual galaxy clusters, which are typically 100 times as massive as galaxies. But weak lensing is weak, and when measuring lensing by galaxies, it's necessary to add them up, to stack them up, and look at many at a time. Okay, so these results with spiral galaxies allow the study of dark matter in a regime, individual galaxies, which has not been possible with weak lensing and does not look like it will be possible in future. And this is important because our model has theoretical predictions for the dark matter halos, for their form, their density profiles, and also for whether those profiles are affected by the presence of a galaxy. And so these results can be used as a way of testing those models. So to summarize, both of these results represent two important ways of studying the dark matter, but they're in very different regimes, the large-scale cosmological regime and the galaxy regime. So these results are important in themselves. They're also important as a sort of proof of concept in the future. They allow us to see how powerful these methods will be with other data sets to do additional work in future.
Okay, that's terrific. Thank you all very much. So we're going to move to the Q&A, and I want to remind everybody that since we are webcasting, we need you to wait for a microphone. Larry has it up here. So when you're ready to ask your question, please identify yourself, say which outlet you work for, which media outlet, and please identify who you're asking the question of. All right, so we'll start here in the room, and then if we can get through the room, we'll go to the webcast. All right, so let's start here with Govert and then Clara.
Govert Schilling, freelance writer from the Netherlands. I have two questions for the CFHT lensing survey. The first one is, what you showed were two-dimensional maps, right? Do you have any information on the three-dimensional distribution of the dark matter? And my second question is, do these results rule out any of the modified gravity explanations for dark matter?
So about the 3D, yes, we do have some information. As Catherine said, we look at the sky in multicolor. Technically, we look at the sky from very blue band, which we call U band, down to Z band, which is not infrared yet, but it's very red. So using 5 filters between these two. Using those filters, we can get an estimate how distant galaxies are with a technique called photometric redshift. And if you come to the technical talks this afternoon, you'll hear more about photometric redshift constraints we have for this survey. So based on that, so combining the distance information for galaxies we have and the lensing information, the answer to your question is yes, we can get some 3D information about mass map. And in fact, we do have a 3D mass map, which we didn't show here, but I think it will be part of the technical talks this afternoon. So, yeah.
And on the testing gravity side of things, so Fergus Simpson, who's sitting back there, is going to be giving a talk on that this afternoon. And because we're probing such large scales, and because we have this multicolour data where we can look at how dark matter is evolving with time, which tells us about what dark energy is doing to it. I was talking about that, the giant cosmic battle between them. We are able to test gravity on these very large scales, and what we're finding is sort of concrete evidence that's supporting Einstein's theory of general relativity on these cosmological scales.
Space.com. And my question is also for you too. You talked about how your results agree so far with theoretical simulations, and I'm just wondering if there's any hints of any kind of difference or divergence between what you predicted and what you saw?
I would say it's much work in progress, because to answer your question, we really need to go into the very, very details of the maps you've seen. So that requires a very, very detailed and careful statistical analysis how the two maps agree. And this is actually work in progress. So far we haven't seen any odd things or any deviation from what we expect, but who knows? I mean, within the next few months, we'll really go to the bottom of the analysis of this. And if there is anything strange in the data, then yeah, we will talk about it. But so far, I would say everything looks like expected. And I should also say we are planning to make all the data public to our fellow astronomers. So if they want to redo the analysis we've done, or continue the analysis and search for more things, they are welcome to do so.
Okay.
Good morning. I'm Camille Carla from Sky and Telescope. I was wondering, Sukanya, how would you go about determining the transition region from which you would determine the scale radius?
Right. The transition region you can determine by looking at the change in the gradient of the phase of the modes as a function of radius. So basically, if you're looking at the phase as a function of radius, interior to the scale radius, the gradient is negative. Exterior to the scale radius, the gradient is positive, and it transitions close to the scale radius.
Can you explain what you mean by the phase exactly?
The phase tells you about the shape of the spiral planform. That is it tightly wrapped or is it loosely wrapped? So as it is becoming more and more tightly wrapped, the gradient is becoming more and more positive. And basically, if you have an atomic hydrogen map, you would decompose that in terms of the shape and in terms of the strength. So the shape is basically the phase, and the strength is the Fourier amplitudes, which we analyzed earlier.
I'd like to mention that I think astronomers are really, really good at coming up with really, really bad names for things. They catch the public's attention, they're very descriptive, but they're usually wrong. And I think this would be a really good time to just stop for a second and say what we mean by a halo. Because if you tell somebody that there's a dark matter halo around a galaxy, the first thing they're going to think is a big ring. And then if they decide to think in 3 dimensions, they're going to think a big shell. But you described a density profile which is peaked at the center and slowly falls off, and then much more steeply falls off, right? So when we think of a halo of a galaxy, it's really much like the galaxy itself, denser at the center and starts to fall off, and then at some point it's just disappearing. So it's really important to keep that in mind when we talk about halos. They're not rings or shells. Okay. Do you have any other questions here in the room? We have some in the webcast? Or okay. Sorry, we'll get a second mic for the next briefing so that we don't have to spend so much time passing it around.
Okay. The first question is from Jan Hattenbach, who is a freelance journalist from Germany, for Ludovic and/or Catherine. How good is the agreement between the CFHT lens results and simulations? The pictures look pretty similar to images of the Millennium simulation, but could you be more specific? Do the data reproduce the assumed abundances of dark matter, dark energy, and ordinary matter?
Yeah, so it actually does very well. So I don't think it's the right place to talk about statistical analysis and all those technical complications here, but it really does work very well. So in a sense, things we can measure, for instance, which is a powerful test, so actually regarding testing the agreement between data and simulation, which is exactly what the question is about, is to look for what we call the power spectrum of the dark matter distribution, or related quantities to the power spectrum, and it's exactly what we expected. So yeah, it does. So far we haven't seen any deviation from what we expect from simulations. Yeah.
Okay, thank you. The second question is from Vanessa D'Amico from Universe Today, and this is for Sukanya Chakrabarty. Could you elaborate on what you look for in terms of the shape of disturbances in the hydrogen disks of the galaxies that you are looking at?
Sure. We're basically, what I'm basically looking at is how tightly wrapped is the spiral, or how loosely wrapped is the spiral. And the scale radius is the region where the gradient in the phase transitions from either having a negative gradient to a positive gradient.
And positive gradient, you mean whether it's getting steeper or less steep?
That's right. That's exactly right. So if it's very tightly wrapped, it's going to have a positive gradient in the phase, and it's going to become, the gradient will become negative as it's becoming more and more loosely wrapped and transition close to the scale radius. And you can do all of this with simply the atomic hydrogen map of spiral galaxies, which we have access to now from large surveys that have been done, such as the THINGS survey that produced stage 1 maps of some 40 spiral galaxies in the local volume.
Anything else on the web right now? Any other questions here in the room? Okay, those of you who've been here before know that when that happens, I start asking questions. All right? So I have a question for Dr. Mandelbaum. Since you take a big picture view of dark matter and will be reviewing the current status of our understanding, right now there's lots of interest in the experiments being done, for example, at the Large Hadron Collider, to try to find dark matter particles, and there's also the searches in deep underground labs. And there's this sense of anticipation that we're going to find the Higgs boson and what that's going to do, but there's also a sense of anticipation that we're going to really get a handle on dark matter. And my question is, are we being over-optimistic? Have we reached a point where there's enough data, or there will soon be enough data, that we really think we're going to get a handle on what this stuff must be and really where it is and how it has affected cosmic evolution?
Wow, that's a pretty open-ended question. So it's really hard to say. I mean, I think people are going about it in the right way, in the sense that, as you alluded to, there are several different fronts on which people are seeking to detect dark matter. I mean, they each have their own specific role. So the cosmological results here, for example, are a way of sort of indirect inference, and obviously direct detection would be extremely interesting, although it has not thus far actually happened. It's only led to limits on the mass and the cross section. So will we soon have enough data to? It's really hard to say, because it depends on what exactly it is, what exactly the dark matter is, which we don't know. But I will say that this multi-pronged sort of approach seems to be necessary if we want to sort of cover all the possible bases.
Mm-hmm. Okay, another question, which I suppose would be primarily for Catherine and Ludovic. is we're going to be hearing in the next briefing about some of the Sloan survey results. And yesterday, some of us went on a press tour to learn about HET-DEX, the new experiment to measure dark energy. And as you described, your maps have information embedded in them about both dark energy and dark matter. So I guess my question is, how do you disentangle them to make sure that you're getting a good read on the two independent components? Because you're looking at the same map and saying you can see what dark energy is doing and you can see what dark matter is doing. And there's all these surveys, some of which say they're doing dark matter and some of which say they're doing dark energy. They're all the same kind of survey. They're getting spectra or colors for lots and lots of galaxies over wide fields, or ever wider fields and ever deeper. So how do you disentangle the two effects, and how do you convince yourself that instead of interpreting the dark matter doing this and the dark energy doing that, you're mixing it up a little bit?
Well, we really need both of these types of experiments, the lensing experiments and the spectroscopic experiments, because they test different things. So what we test here, we're mapping out dark matter at different epochs in the history of the universe. And we're talking about dark energy and this battle between them. Dark energy essentially slows down these structures of dark matter forming, because it's sort of fighting against the gravity of the dark matter. Now, what the spectroscopic surveys, the SDSS and HET-DEX do, is they're looking at the geometry of the universe and how fast dark energy is stretching space, this accelerated expansion of space. But they can't test how that impacts on dark matter. Now, one explanation of dark energy is simply that we need to go beyond Einstein's theory of gravity. That we understand GR very well on the scales that we've tested it so far, but we haven't really tested it on these larger cosmological scales. And one answer might be that we just need to add something more to Einstein's theory of general relativity. And we can't test that with the SDSS because it's not testing gravity, it's testing the geometry of the universe and how that's changing with time. So how do we disentangle the two? Only by doing both lensing experiments and spectroscopic experiments, and that's why the European Space Agency is in the next decade going to be launching a satellite called Euclid that can do both of these experiments simultaneously, the lensing measurements of the dark matter and how that's evolving with time, and also the spectroscopic survey to see how that's, and both using both of those methods, then we can disentangle the two.
Very good, very interesting. Has anything else come in online? Nope. All right, well, it sounds like we've exhausted all the questions. I can't think of any others right now, although I will as soon as we're finished, I'm sure. So I'd like to thank our speakers for very interesting presentations, and Dr. Mandelbaum for giving us broader context and where it's all going. We have two more briefings today. We have one at 11:45 that in some ways continues the same theme, not necessarily just about dark matter, but the idea of large-scale surveys of the universe and what they're telling us about our galaxy and other galaxies. That's at 11:45, How to Build a Milky Way. And then at 2:30, we have the first results from LOFAR, the Low Frequency Array, a new radio telescope that's been built in Europe and is finally making observations. So I hope you'll be back for those two. And again, I thank you all very much, and we'll see you at midday.